Okay, so let's start today's session. Hello everyone, I am noc22-ee119 from IISc Bangalore from the Electrical Engineering Department. I am a PhD student over there, and I will be taking these weekly TA sessions for this pattern recognition and application course. So in these sessions we will basically try to solve some problems related to that week's topics. So basically today we'll be focusing on problems on the feature extraction part. So I'll take some basic problems and I'll solve it. I'll show you how to solve it, and if you have any doubts you can post that in the chat. So after each problem I'll take up the questions that will be there in the chat. So let us get started with the first problem. So all of you must have gone through the week 1 content which are on feature extraction. So the first problem that we have here is, which of the following feature corresponds to the boundary based features? So as you know, boundary based feature means these features describe the shape of the object or boundary of the object. So for example, if we have some object like this, so the features will be something that will describe this outer boundary or outer line, and these features have nothing to do with the inside content. We'll just focus on the outer boundary. Those are the boundary based features. So here the first option that we have is intensity. So as we know, intensity is basically a feature of the region enclosed within the boundary. So it is not a boundary based feature. But chain code is something where we represent a boundary by piecewise linear segments using their length and direction. We represent the boundary. So that is basically a boundary based feature. Next is polygonal approximation. This is also a boundary based feature, because in this case we take an arbitrary boundary of an object and we try to express that as some polygon. By some polygonal approximation we try to represent that boundary. So this is also a boundary based feature. And last is signature. That is also, as you know, is boundary based feature, because there also we try to find the distance of each point on the boundary from the centroid and try to plot a graph for that. And so that is also related to the boundary based feature. So for this problem, all the three options, chain code, polygonal approximation and signature, all three belongs to the boundary based features, whereas intensity is a region based feature. So the right answer for these question will be 2, 3 and 4. So if you have any question related to this boundary based feature, what is called boundary based feature, you can post it over here. Otherwise I'll move to the first problem, which is on chain code. So here in the problem 2, we are focusing on one particular type of boundary based feature, which is the chain code. So we have been given this object, particularly the boundary of that object, and we have to derive the chain code for this. And it has been said in the question that we have to assume 8 connectivity. So the connectivity directions which should be there has been given in this figure. So the east direction has been encoded with 0, and in anti-clockwise direction we have 1, 2, 3, 4 till 7. So these are the 8 directions we will consider while performing the chain code, and we have to move in the clockwise direction. So here this point is marked as the starting point. From here we will move in the clockwise direction. So in this way we will move to form the code. Now let me make the figure a bit bigger. Yeah. So here our starting point has been given as this one. So the first segment that we have is this. So we can see the grid already imposed on the figure. So we'll take each cell of that grid, each side of this grid, like this portion, to be unit length. So the first segment that we take is this segment. So it is going towards the, you can say, southeast direction. So if we consider the codes that we already have for the 8 connectivity, this is that particular direction. So the code is 7 for this. So for the first segment, our code will be 7. The next segment is also the same. So we have again 7, and the third segment is also same. So we have 3 7s. Now the next direction is towards the south, this portion. So in following the 8 connectivity, this is encoded as 6. So this segment will be coded as 6, and the next 3 segments, this one and this one also, will be coded as 6, because all are the same southwards direction. Now the next one that we have is this segment. This is this segment. So as you can see from the connectivity diagram, this is the direction. So this, the code is 4 for this. So we have 4 here. Then the next 1, 2, 3, 4, 5 segments are also in the same direction. So all of them will be encoded by the same code, which is 4 in our case. Okay. Now the next direction is towards the north. Following this connectivity, again we have the code as 2. This is also 2. This is also 2. Now we have this one, northeast. This is 1. So 1, 1 and 1. So we have reached the starting point again, and now we have the entire code. So if we write down the final chain code, that will be 7 7 7, then 4 6s, then 4 4 4 4 4 4, this is the code. So if you go back to the options that were given, so this one is, you have 3 7s, then 4 6s, then 6 4s. So 3 7s, 4 6s, then 6 4s, 4 2 3 1s, 4 2 3 1. So option C is your right answer. So that is the chain code for this particular figure. So I don't see any questions. I think I assume everyone is clear with this one. So I'll move to the next problem. So as you have seen, when you derive chain code, so let us go to this one. When you derive the chain code, now if this chain code is translation invariant, so even if you shift the figure towards the right, towards top, or to any direction, whatever are the codes that you have got for the consecutive line segments, those will be the same only. So you will get the same chain code. So it is translation invariant. But if you rotate the figure by some angle, then the then the codes might get changed. For example, if you just rotate this figure such that the first segment, which is this one, becomes this, then the first number of the code will change from 7 to 6. It will be changed, everything will get changed. So to combat that issue, we use what is called the differential chain code. So now in this problem, the third problem, we will try to find the differential chain code for that same figure. Here also we are assuming 8 connectivity, and we are moving in the clockwise direction in the figure, but for counting the differential direction we will have to use anti-clockwise direction. So if we have at so in this coding figure we will have to go in the anti-clockwise direction. So if we have direction 0 for one segment and direction 2 for next segment, then the number of rotations needed for that change will be 2 in this direction. We will have to consider. Okay. So let us look into this. So I'll copy the chain code first, so that will be easier for us to derive the differential chain code. So this was the chain code for this figure. Now we will have to find the differential chain code. So for finding the differential chain code, what we need to do is, for going from one line segment to the next line segment, how many number of anti-clockwise rotations are needed in this 8 connectivity figure, that is what we need to encode. So here the first direction that we have is 7, and the next line segment that we have is also 7. So going from 7 to 7, we don't need any rotational steps. So the first differential code value will be 0. Again we have the direction 7. So for going from this second 7 to the third 7, we also don't need any rotational step. So this is also 0. Now we are at this 7, and we will next go to 6, direction 6. That is, we are now in this segment, we will need to go to this segment. So here you have 7 and here you have 6. So you will have to go in the anti-clockwise direction. So like this. So you will need to have 1, 2, 3, 4, 5, 6, 7. 7 rotational steps you will need to have to go from 7 to 6. So the next value will be 7. Again we are remaining in the direction 6 itself, so we don't need any rotation. So 0, 0, 0. Now we are at this point, and the next direction that we need is this. So from 6 we need to go to 4. So here we have 6 and here we have 4. So to count in the anti-clockwise direction, 1, 2, 3, 4, 5, 6. We'll need 6 rotational steps to go from 6 to 4. So we have 6. Again we have 0, 0, 0, 0, 0, because we are maintaining the same direction 4 throughout these 6 segments. So it will be the rotational steps needed to go from one segment to another will not change, it will be 0 throughout. Now again we have the direction as 4, so we are at this segment and we need to go to the next segment, which is the 2 segment. This one. So here is 4 and here we have 2, and we will have to go in the anti-clockwise directions. So, how many steps will be needed? 1, 2, 3, 4, 5, 6. So, we have 6. Again we have 0, 0, 0. Then the last transition is from this segment 2, we will have to go to this segment, which is direction 1. So, from 2 we will go to 1. So, here we have 2 and here we have 1. If we go in the anti-clockwise sense, that is 1, 2, 3, 4, 5, 6, 7. So, we have 7, again 0, 0. Now we have reached this segment, but the first segment, the change to the first segment is yet to be computed. So, we are at 1, which is here, and the first segment that we had, this one, that is this one, was 7. So, we need to now go from 1 to 7. So, here we have 1, here we have 7, that means 6 rotational steps. So, we have 6. So, the entire differential chain code that we have for this particular figure comes out to be this: 6 0 0 7 0 0 0 6, then 5 zeros, then 6 3 zeros, 7 0 0. This is the final differential chain code for this particular figure. So, I will stop for 1 minute here. If you have any questions or doubts, you can ask. So, to see in this options, this will be option C only. Oh no, sorry. So, this will be option this one is 6 0 0 6 0 0 7 0 0 7 0 0, then 6 5 zeros, 6 5 zeros, 6 0 0 6 0 0 7 0 7 0. So, option A is the correct answer for this. So, since we do not have any doubts, I will move on to the next problem. So, once we have the differential chain code, so original chain code was translation invariant but not rotation invariant. Now, we went to differential chain code. Since we are just considering the number of rotations needed to go from one line segment to the next line segment, so even if you rotate the figure, that change remains the same. So, your differential chain code won't change even if you rotate the figure. So, your differential chain code has become rotation invariant, and it is already translation invariant as well. But the thing that still remains is what point you choose as the starting point, that will change your code. So, if you start from this point, you will get one code, but if you start from this point, you will get some other code. So, the next thing that we have to combat this issue is the shape number. So now we will compute the shape number considering the largest number using the differential chain code of this figure, and we will again assume 8 connectivity and moving in clockwise direction and counting differential directions in anti-clockwise direction. So we already have the differential chain code. Let me get it back. So 600 700 7000 So this is the differential chain code for this. Now to consider the shape number, we don't assume this code as a chain anymore. We will consider this as a cycle. Like after this we have again this is in a cyclic fashion the numbers are put. So there is no particular starting point. Then here we are asked to derive the shape number using the largest number. So then after making it cyclic, we will have to choose such a starting point so that the number we form becomes the largest possible for this combination. Now if you select the starting point that way, then since the largest number of this particular set of digits is unique only, so you will get a unique code whatever be the in whatever direction you whatever point you originally started coding the differential code, finally you will end up with the same shape number. So if we consider this particular case, we will have to get the largest number out of these figures. So we can see here we have 6, 0, 7. These are the 3 unique digits. So to have the number as the largest one, we will have to start the number with 7. So it can start either here or here, but after this point, this one, you have 3 zeros, whereas after this 2 0 and then 6. So if we start at this point, this will give us the largest number, and that largest number will be 7006 007 000 6 000 6000. So this is the largest number out of this cyclic code. So this is the shape number for this 700600. So we have 700600, then we have 7000 6, then 5 zeros, then 630. So option D will be the correct answer for this particular problem. So this is the shape number. So with this we have achieved all translation invariance, rotation invariance, as well as invariance to the starting point. Whatever we consider for all these things, we will get the same code or the same feature vector, we can say, for this particular figure. So this is the boundary based figure. So with these problems we have gone through all the types of boundary based features: chain code, differential chain code, and the shape number. So now the next question that we have is, which of the following statement is correct? The first is chain code is translation variant. So as we saw just now, while some time before, while coding the chain code, that wherever you translate the shape, the chain code is not going to change because the direction of the segments will not change. So chain code is not translation variant, it is translation invariant. So the first statement is not correct. Next is chain code is rotation invariant. rotation invariant. So it is not rotation invariant. If you rotate the figure, then the direction of the lines will change and your chain code will change. So chain code is not rotation invariant. Third thing is differential chain code is rotation invariant. That is correct, because even if you rotate the figure by any amount of angles, the relative degree of rotation that you need to go from one line segment to the next line segment, that remains the same. So differential chain code is rotation invariant. So this is the correct option for this. Then we have one more question from this invariance aspect. This is for representation of a circle, radius and center are being used as features. Then which of them is translation variant, which is invariant, that we need to tell. So if we take one circle, let's say we have, this is our x axis, this is our y axis, and this is my circle, and this is the center point for this. Let's say the coordinate of this center point is x1 and y1, and the radius is, let's say, r. So now we translate the figure, translate this circle, and we, let's say, put it over here. Put it over here. So the center has come here. So the new center has become x2, y2, but the radius is still r. So you see, when we translate the circle from one position to another position, the radius will not change, that will be the same only. So radius is translation invariant, but as soon as you shift the circle, the center point shifts. So initially it was at x1 y1, now it has come to x2 y2. So the center point is not translation invariant, it is translation variant. Where you are positioning your circle, the center point will change depend on that. And so here the options that we have is radius is translation invariant, of course that is true. Then center is translation variant, yes, that is also true. Then radius and center both are translation invariant, that is false, because center is not translation invariant. So the correct option will be this one, both A and B. So both of them are correct only. That is radius is invariant to translation, but center point is not. Moving on to the last problem on boundary based features. This is on the signature. So here we have been given one particular signature, and we need to tell which particular shape which particular geometric shape this signature belongs to. So so we have four options over here: circle, square, rectangle, and equilateral triangle. So let us try to draw the signature for each of these shapes one by one, and then we can finally decide which this particular shape belongs to. So here I'd like to ask you first. So if we take a circle, can any of you post in the chat what will be the signature for a circle? Anyone, if you want to try out, what will be the signature for a circle? Okay, so let me define the process of deriving the signature once for an arbitrary shape, then I think you can try out for circle. So let's say we have some arbitrary shape like this, and we need to determine the signature of this particular shape. So for determining signature, we have this one as the reference direction. This is our reference direction, and let's say this is your centroid for this particular shape. So how do you go about computing the signature? So what you do is you take one point on the boundary, let's say this point, and you join this one from the centroid to that particular point on the boundary, and you compute this length, the distance of this boundary point from the centroid. This we did define as L. Now first we will define it as L, and we will have to also compute this angle with the reference direction. So the angle that this particular straight line is making with the reference direction, that we will have to take. So let's say we define that angle as theta. So as you can see, if you choose this particular point, then the length is this much, but if you choose this point, then the length becomes this much, which is much smaller than the first segment. So depending on at what theta you are measuring the angle, that length will keep on changing. So we can say that this length is a function of that theta. So we will write that as L within bracket theta, that is L, which is a function of theta. So now you will have to take a number of points over the entire boundary and at different theta angles, and you will have to measure that distance of that particular boundary point from the centroid, which is the L theta for that particular point. So let's say if you have points at theta 1, theta 2, theta 3, like that to theta n, you will have to compute the corresponding lengths L1, L2, L3 to Ln, that is the length, the distance between the centroid and the point on the boundary at angle theta with the reference direction. Now once we have all these values for L at different thetas, then we can go for a plot where our x-axis is theta and y-axis is L theta. And if you plot that L theta across with respect to theta in such a plot, you will, whatever figure you will get, that is basically the signature for this particular shape. So this is the process of computing signature, which is also, as you can see, a boundary based feature. So now based on this particular process, you have a recap of this process. Now can any of you tell me what will be the signature of circle? Yeah, we have got one answer from Ayush. Straight line, absolutely correct Ayush, that will be a straight line. Yeah, parallel to x-axis, straight line parallel to x-axis, or you can say theta axis here. Since you are plotting against theta, so it will be parallel to theta axis, right? So I'll explain it for the others. So let's say we take the circle shape. Let's say we have a circle like this, and this is the centroid for this. So our reference direction will be like this. So let's say first we take this point. So we have to compute this distance, which is basically r, and we have this angle. Now let's say we take another point over here. So you know, this is always the radius of the circle. These are the radius, so this will also be r. However, we have changed the angle. Let's say initially if I tell that as theta 1 and this has now become theta 2, but the distance is still r. So whatever point you take on the boundary, if you want to compute the distance from the center to the boundary, for a circle that distance is always constant. So you will always get r wherever you put that point on the boundary. So if you now plot for all possible theta, these particular distances, you will always have that value as r. So you will get a straight line like this parallel to theta axis, which will be at the value of r. So this is the signature for the circle. Now next let us move on to square. So let's have a square like this. Now we need to find the signature for square. So let's take the centroid here and the reference direction is here. Now let's say first we'll take points on this segment. So when we are taking points on, change the color. When we are taking points on this segment, the distance, this distance from the centroid to one of boundary point will keep on increasing, right? It will keep on increasing till you reach this particular vertex point. So as you increase the angle theta from 0 till this particular position, your length or this distance of the centroid to the boundary point will keep on increasing. Now after this, when you go from here to here, that is on the top straight line, from the right vertex to the left vertex, first when you go till this middle point, you can see the distance is decreasing. So this is this middle point, that dotted line I have drawn, that is basically the perpendicular I have drawn from this centroid on the straight line. So that is the minimum distance. As we know, if we draw the perpendicular from a point, that will be the minimum distance. So this is the minimum distance. So on the right side the distance gradually increases, the left side the distance gradually increases. So if when you are going from this particular point to this point, first the distance will decrease, it will be the minimum at this midpoint, then again it will keep on increasing and increase the maximum point here. Same thing again will happen for this vertical segment, again for this horizontal segment, and lastly when you are moving from this particular vertex to your initial reference position. So this is again the from the vertex from the centroid along the reference direction, this is again perpendicular. So this is the lowest distance. So as you go from this vertex to the reference direction, your distance will keep on decreasing. So considering all this, if you now plot theta, L theta across theta, so initially when you are moving from the 0 angle, your distance is first increasing, then your distance is decreasing till this midpoint, and since this is a square, this decrease, the lowest distance that you get here at the perpendicular will be the same as the distance along the reference direction, along this point. This is the same direction, same distance. So your distance will decrease to this same level, and again it will increase to the again same level. Then for the left, this vertical direction, again it will decrease first, then increase, and then for this one again you have the same thing, and lastly for this half segment below the reference direction, here your distance will keep on decreasing. So, finally, we will get something like this. So, since you have 4 vertex here, we will have the maximum distance at 4 points. That is what we have got here, 1, 2, 3, 4 points where we have got that maximum distance, and 4 points where you have also minima for all 4 line segments, and this is basically the continuation of these two halves. So, you have basically got the minimum distances at these 4 middle points. So, this is the signature for the square. Now, when you go from square to rectangle, what change you make is just your height and width becomes different. So, this is what you have a rectangle. So, as you can obviously guess, the overall structure will be similar only for the signature. The only thing is the minimum distance that you have along these vertical directions will be more than the distance you have along this horizontal direction. These differences will be less and these minimum difference will be more. So, if you try to plot a similar figure with that, so what you will get is initially your distance will increase, then here what along the reference direction, whatever your minimum distance was there, you will reach less along this direction, basically half of that in that direction. So, your distance will keep on decreasing till this point, again it will increase, again decrease, increase. Oh, sorry, this is again we are along the vertical direction. So, it will not decrease to that point. So, for the horizontal part it will decrease till this part, but when again we are in the vertical shape, this distance is larger. So, we will just have this much, again this much, and lastly this much. So, this will be the signature for a rectangle. So, as you can see, the signature that is given in our question, that is for a rectangle actually. So, option C is the correct answer for this. But let us also try to define the signature for an equilateral triangle. That will complete the question. So, here let us take one equilateral triangle, and again your reference direction will be along this. So, here also first your distance will increase as you go from here to this till this vertex, then at these, so actually I should have like this. Let me redraw it, it's not actually correct. So, you have your reference direction something here, this is your perpendiculars. So, if you start from this direction, initially your distance is increasing, then your distance will decrease till this point, again it will increase, again it will decrease, increase, decrease. So here as you see you have 3 vertices, so you will have 3 peak points in the signature graph. So if you draw it, initially your distance will increase, go to some point, again it will decrease and increase, decrease and increase and decrease. So you will have 3 peaks, this is L theta. So you will have 3 peaks and this will be the signature for your equilateral triangle. So we have derived the signature for quite a few shapes. So I think it is now clear to everyone how to do the signature based questions. So this was some problems on the feature boundary based features. The next, so if anyone has any question, I don't see anything in the chat. Okay, so I'll move on. So the next problem that we have is on the learning aspect. So which one of these 2 statements is true, that you need to guess. The first statement is, in case of supervised learning, known patterns or labeled data are used for training. And the second statement is, in case of unsupervised learning, additional step of data agglomeration is done based on similarity. We will have to tell which one of the following is true. So any guesses? Any guesses from anyone? I have the answer from Ayush. Yes, this is option C. Both A1 and 2 are correct. So in supervised learning, you are basically given patterns or features and you know the class of that feature. So you have, that is called the labeled data. You have the feature vectors as well as you know the label for that particular feature vector. Now you take those feature vectors and you try to train your classifier or whatever model you are trying to learn, that you can train using those known data as well as for which you know the classes as well. But in case of unsupervised learning, you are given the data, you don't know the class of each of those data. So first what you need to do is you have to cluster those data in different types. Once you have done that, the remaining process is the same. You can go for the similar approach as the supervised one. And the clustering or agglomeration that you do is basically based on similarity. So you will assign similar data to the same cluster. That is the approach in case of unsupervised learning. So initially you are not given the actual labels, so it's your responsibility to determine the to cluster or group the similar data into similar groups. So whatever you put in one particular group, all of them should be similar to each other. Whereas if you take any 2 examples, one from group A, one from group B, that should not be similar. The similarity should be much lower as compared to 2 elements from the same group. So within class similarity should be much more as compared to between class similarity. That should be as less as possible. You have to group the data in that way. Then you can go for the similar approach as the supervised learning. We are at the almost last part of this TA session today. The last problem that I have here is this one. So here you have been given 3 particular patterns and you will have to say which one of them are similar. So this is basically just 4D feature vectors or 4-dimensional feature vectors or 4-dimensional patterns, whatever you say. So if you go in a 4-dimensional space, all of these will be a point. So we know that to determine the similarity between any 2 points in a Cartesian space, we can we can consider the Euclidean distance between the 2 points. So we can try to see what is the Euclidean distance between P1, P2, P1, P3 and P2, P3, and based on those distances we can determine which one of them are similar. Similar ones will have much less distance among them, and even if they are exactly the same, then the points will be coincident and the distance will be actually 0. So based on that distance we can determine. So first for that we need to calculate the Euclidean distance. So let us say if you have 2 points x1, y1, z1, that is your first point, and you have another, this is your, let us say P, and let us say Q is x2, y2, z2. So we all know what will be the Euclidean distance between them. That will be root over x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. This is the formula for the Euclidean distance between these 2 points. So now if we consider the distance between P1, P2, so we have root over, so the first coordinate is same for them, 3, 3. So the difference x1 minus x2, that, so here you can say this is x1, y, P1 is x1, y1, z1, and one more coordinate is there, let us say t1, x1, y1, z1, t1, and p2 is x2, y2, z2, p2, z2, t2. So the first element will be x1 minus x2 square, but both of them are same, so we have 0. The second element is also same, again 0. Now the third element is 5 and 6, so difference is 1. So once we have 1. Last element is again same, we have 0. So the distance we have is 1. Now let us go for P1, P3. Here, what will be the Euclidean distance? First coordinate is 3 for P1 and 104 for P3. So the first element in this formula will be 101 square. The difference is 101 and we have 101 square. Then similarly the next element will also be 101 square because we have 4 and 105. Then we have 5 and 106, so again 101 square. And lastly we have 10, 10, so we have 0. So the final distance, Euclidean distance that we have is 101 root 3. So if you take 101 square as common, you can take 101 out and you have root 3. And the last combination that is remaining is P2, P3. Computing in the similar fashion, we have 101 square plus again 101 square plus here we have 6 and 106, so 100 square plus 0. You can compute the value for these also. So we can see if you compute all these distances, the first one P1, P2 is only 1, whereas the other two distances are much higher or orders of magnitude higher. So we can say that P1, P2 are similar because the distance between them is just 1, whereas P1, P3 and P2, P3 are very different because the distance between them is much higher. So here I have, so this particular problem we have P1 and P2 are similar. So here we considered the Euclidean distance as the metric for this, and we computed the difference. This way you can determine this is one way of determining the similarity between the different patterns that you are given. So once you determine the feature vector for some example, using this type of approach you can determine which all feature vectors are similar, so the corresponding objects will be in the same class. So this is one way of determining the similarity. So these were the problems that I planned for the first week. So any questions if you have from this part, you can ask now, and then we will meet in the next session with the week 2's problems. So any questions you can post it in the chat. We have 2 more minutes in today's session. We can answer, we can discuss anything. Yes.
Ma'am, I had one doubt in that polygonal approximation.
Yes.
In there, we have this function of like criteria function, where we split the boundary of the shape based on points.
Huh.
So in that we choose points that is the maximum distance from the straight line, and in video it said that that distance should be greater than the threshold.
Yes.
So I wanted to ask, like, what is that threshold? Like, what it actually means?
So threshold means it's a heuristic quantity. You specify it. There is depending on your application, you specify a threshold. So let's say, let's take one figure. Let's say you have this type of shape, and you want the polygonal approximation for this. So let's say you have initially taken these 2 points, joined this, and you have now you compute the maximum distance from this line to all points in this half. Say in this half first we are computing, so this is the maximum. So here and around here you have the next splitting point. Now if you consider this particular portion, if you take the distance here, so we will have to join this. So if you take the distance here, so you can see there is not much variation in this portion. So this is almost already become a straight line. So it's because I didn't draw it correctly, and let me just redraw. Let's say the shape is like this, and you have your joining line as this. So you have almost reached the boundary. So whatever is the maximum distance, that is very small. So it depends on what is the resolution that you want. So if you don't need this much change to be accounted for by different straight lines, so you set that threshold such that this will come as one particular this will come in one straight line itself, will not segment it further. But if this much distance also, this much variation in the boundary also matters for your application, then you will have to set the threshold such that you again get a point over here, and you can get further more accurate approximation. So depending on your particular need, how much exact you need that polygon to match with the actual boundary, you will put your threshold based on that. So if you put the threshold much higher, you will have a much crude approximation. You will be much you will lose a lot of details, but you put that threshold much lower, you will get a more detailed contour, more match, the match will be more. So based on that you set that threshold. Does that give you some idea?
Yes, ma'am. Thank you.
Okay, so I don't see any more questions and we are also out of time today. So thank you everyone for joining. Let's meet again in the next week with the next set of problems on week 2 sessions. Thank you.